One line of SQL. The same query went from 4.2 seconds to 3 milliseconds. You probably know the headline already. An index makes lookups fast. But that is where almost every explanation stops. It says the database uses something called a B-tree and moves on. So here is the question that actually bothered me. The table has 5 million rows. Finding one takes about 3 steps. 3. Not 3,000, not 3 million. Why 3? And why does that barely change when the table gets enormous? It is not a coincidence. It falls out of the shape of the thing. Let's open it up.
Here is the floor. Without an index, your table is a pile of rows on disk in the order they arrived. Nothing is sorted. So when you ask for one customer by email, the database has no idea where that row is. Its only option is to read all 5 million. That is the 4.2 seconds. Add an index, and the same query reads about 3 things instead. That much you know. What you have probably never seen is what is inside that index, because 3 is a strange number. Reaching any one item in a 5 million row pile in 3 steps sounds like cheating. It is not. It is a structure. Let's build it. Start with the obvious idea, because watching it fail tells you why the tree exists. Just keep the emails in a sorted list. If everything is sorted, you never read all of it. You jump to the middle, before or after. Throw away half. Jump again. Keep having. For 5 million rows, that lands in about 23 steps. Genuinely fast. On paper, the same class of fast as a B-tree. So why not just do that? Because of rights. One new customer signs up. Their email belongs in the middle. To put it there, every row after it shifts one slot over to make room. Millions of rows moved for one sign-up. A sorted list is fast to read and catastrophic to change. And a real database changes constantly. So here is the real problem. The structure has to stay sorted while people are writing to it. That tension is what produces the tree.
One thing has to be right in your head first. When you picture a tree, you probably picture little circles holding one number each. Forget that. A node is not a number. A node is a page. A page is a fixed-size block of disk, and in Postgres, it is 8 kilobytes by default. That is the smallest amount the database will read. It never fetches one key. It fetches the whole page. So the question is not how many comparisons do I do. Comparisons are free. They happen in memory. The real question is how many pages do I fetch. Every hop down the tree is one page pulled off disk. The hops are the cost. Everything else rounds to 0. And once you see that, the design writes itself. The page is coming off the disk anyway, so fill it.
Now compare. On the left, a classic binary tree. 2 children per node, which means 1 key per node. So you spend an entire 8 kilobyte page, one whole disk read, to learn a single yes or no. Go left or go right, and you pay that 23 times. On the right, the B-tree. Same page, but crammed full. For a short value like an email, roughly 200 keys fit in one page, each with a pointer to a child page beneath it. So one page fetch does not split the problem in 2, it splits it into 200. That is the whole trick. There is nothing else behind it. The B is not for binary. This is a fat, wide, shallow tree, shaped that way for one reason. Disk reads are expensive, and the page is the unit you pay in. So make every page you fetch do 200 times more work.
And now the depth falls out. It is not a design decision. It is arithmetic. One page at the top holds 200 pointers. Each points at a page holding 200 more. That is 40,000. One more level. 40,000 times 200 is 8 million in 3 levels. Our table has 5 million rows. It fits. So 3 hops. That is where the 3 comes from. Against 23 for the binary tree. Same data, same disk. 8 times fewer trips to the disk because we picked the right width. And here is the part I find beautiful. Grow that table 200 times over to 1 billion rows. You add 1 hop, 4 levels instead of 3. The tree gets wider, not taller, which means your index does not meaningfully slow down as your data grows. That is why this thing has run every database on Earth for 50 years. Now, one detail, and it explains everything your index can do. What Postgres uses is not quite a plain B-tree. It is a B+tree. The difference sounds tiny. It is not. In a B+tree, the nodes on the way down hold keys only. Signposts, no data. All the real pointers to your rows live in the bottom row of the tree, in what we call the leaves, which means two things. First, every lookup costs the same, 3 hops every time. There is no lucky row near the top. The tree is perfectly balanced. Second, and this is the good one, because the leaves hold everything, and they are the bottom layer, they can be chained together. Each leaf links to the leaf on its left and the one on its right. So the bottom of your index is not just a tree, it is also a sorted list, end to end, that you can walk in either direction. Hold on to that. Watch what one index on one column can answer. This exact email, descend 3 hops, done. Everything after a date, descend once to find the start, then walk sideways along those links. Between 20 and 30, 2 ends, 1 walk. Order by email, first 10, this one is my favorite. The database does no sorting at all. The leaves are already in order. It walks to the start and takes 10. Now the honest part. Starts with SARA. A prefix is really a range, so in principle the tree can do it. But in Postgres, unless your database is in the plain C locale, a normal index will not be used for that. You need a second index declared with a thing called text pattern ops, and that one cannot do your less thans or your order bys, so you would need both. It is a real sharp edge, and almost nobody mentions it. And then the wall. Ends with mail.com. No index can help. The tree only knows how to start from the beginning of a value. Give it the end, and it has nothing to grab onto. Every yes here is the same 2 properties, sorted keys, linked leaves. The no has neither. Enough theory. You can see every word of this in your own database. The tool is Explain Analyze. Put it in front of any query, Postgres runs it, then tells you exactly what it did. Here is our query on the table with no index. Sequential scan on customers. That is the pile of rows. It started at the top and read the lot. Now the line I want you to remember. Rows removed by filter. 4,999,999. It looked at 5 million rows and threw away all but one. That line is not a warning. It is your 4.2 seconds spelled out. When somebody says run explain on your slow query, this is what they want you to find. Now add the index. 1 line. The table does not change. The query does not change. Run the same thing again. And the plan is different. Index scan, using our index. Let me decode the numbers because they trip everybody up. Cost, 0.43, ... 8.45. Startup cost and total cost. And here is the catch. They are not milliseconds. They are not any unit of time. They are the planner's own made-up units for comparing one plan against another. Do not read them as speed. Actual time is the real thing, and that is in milliseconds. But the word to look at is this one, index cond, condition. The last plan said filter. That one word is the entire video. Filter means I fetched the row, checked it, then threw it away. Index cond means the tree took the condition and went straight to it. It never looked at a row it did not want. And to be straight with you, 3 milliseconds is the whole trip. Your app, the network, the round trip. The lookup itself is a fraction of a millisecond. There is one better, which almost nobody uses on purpose. This query only asks for the email column, and email is the thing the index already stores. So the database has a thought. Why open the table at all? Everything you asked for is already in my leaves. That is an index-only scan. Look at the last line. Heap fetches, 0. Heap is just the name for the real table on disk. It never touched it. And notice what is missing. There is no sort step, even though we asked to order by email. The leaves were already in order. That is the linked leaves caching out. 2 honest caveats. It only works if you ask for columns the index actually holds, and it needs a maintenance job called vacuum to have marked those pages clean. Otherwise, Postgres quietly goes back to the table for every row, and you lose the benefit with no error telling you. Check heap fetches. If it is not 0, that is why. So now the bill. Remember the sorted list where one insert shifted millions of rows? Here is how the tree fixes that. Every leaf page has a bit of empty room. A new row arrives and goes in the gap. No shifting. But eventually a page fills up, so the page splits. It becomes 2 pages, each about half full, and the parent above gets a new key pointing at the new one. If that parent is full, it splits too. That is how the tree grows a level. It stays balanced by splitting, not by shifting. That is the answer to the sorted array. But count what one insert really costs. The row itself is one right. Then every index on that table is a separate tree, and each one has to be descended and updated, or it would be lying to you. 6 indexes? One insert just became 7 rights. This is why index everything just in case is such bad advice. You are not adding speed. You are buying read speed with write speed and disk. An index nobody queries is pure cost.
Which brings me to the question I actually wanted to answer. When is a B-tree the wrong tool? Postgres ships 6 index types. pgvector adds 2 more, and almost everyone only ever types the default. Quick tour. B-tree, the one we just built. Sorted, ordered, ranges. GIN, for when one row contains many values. JSON documents, arrays, full-text search. Remember ends with mail.com, the one the B-tree could not touch? That is GIN category. GIST, for shapes and overlap. Which of these things are near each other? This is what PostGIS uses for maps. If you do geospatial work, you have been using a GIST index. BRIN, for gigantic tables already roughly in order, like time series logs. It stores the smallest and largest value for each block of the table, so it can skip whole chunks. A tiny index for a huge table. Hash, equality and nothing else. And HNSW and IVVF-flat from pgvector for nearest neighbor search over embeddings. So here is the landing. B-tree is the default, and it deserves to be, but not because it is always right. It is the default because ordered access, ranges, and sorting are what most queries want, most of the time, not all of the time. Knowing the other 5 is knowing when you have hit its edge.
The whole thing in 4 lines. A node is a page, so you fill it with 200 keys instead of 1. A fanout of 200 gives 3 levels for 5 million rows, and multiplying the table by 200 costs 1 more hop. B+tree means the pointers live in the leaves, and the leaves are linked, which is why ranges and order by come free. And splitting is how it stays balanced under writes, which is why 6 indexes turn 1 insert into 7 writes.
If that opened the black box, hit like and subscribe. Here's the thing to take away. An index is not free speed. It is a trade. You buy fast, ordered reads, and you pay in disk and in write throughput. So index the columns you genuinely filter on, join on, or sort by, and nothing else.